Divergence is a pretty important concept in vector calculus. So you have a vector field, let's say in 2D you have f of x, y evaluated at a point, and it ends up making a vector. And here I'll use p for the first component, so p of x, y, and then q of x, y. You could also have it in 3D. So right, I could have a vector field in 3D, so x, y, z equals p vector x, y, z, comma q x, y, z, comma r of x, y, z. And then close the vector. All right. So the divergence is supposed to be kind of the amount of arrows flowing out of a point. In the next two videos, we actually have a nice intuitive derivation of, in 2D and 3D using a box and flux and shrinking the box down. That's the idea. So they're both written like this, though. So I have this upside down triangle symbol, dot product, f. So the upside down triangle, it's known as del, known as nabla. It's a Greek harp, and also at del or something. I don't know if delta backwards. So it's a nice shorthand. Another way to write it, which I hardly ever see anyone use, is divergence of f. This is a much nicer shorthand. And right, so the nabla, you treat it as a vector. So I'll do the 2D one first. So if I have partial x, partial y, and I dot that with the vector f, well, that's vector p of x, y, comma q of x, y. So when you dot product, right, you individually multiply the components together and then you add them. So if I'm treating this like a vector, it's partial x times p. So partial p partial x. Then I'm going to add partial y times q. So plus partial q partial y. All right, so that's the idea. It's a nice shorthand. This vector in 2D means vector partial x, comma partial y, close the vector. In 3D, we then have partial x, comma partial y, comma partial z. Let's make that a little pointier. Dot product, the f vector field in 3D, which is p of x, y, z, comma q of x, y, z, comma r of x, y, z. Individually dot the components. I have partial x times p, so partial p partial x. Add the components that you're dotting together, so partial y times q. So partial q partial y plus, and then we have partial z times this r function. So partial r partial z. All right, so those are the definitions. It's kind of where the shorthand comes from. That is a dot product. And then it's the amount of arrows coming out of a point in the vector field. And so intuitively, we're going to figure that out in the next two chalkboards, one in 2D, one in 3D. And it's how much is kind of flowing out of a box divided by the area or volume of that box. This video is an intuitive explanation of how the divergence got its formula and kind of what it means. So let's go ahead and get started here. So let's say we've got a vector field, f of x, y. It's two-dimensional. And then, right, it's going to have two components here. So it's going to have another function, p of x, y, for the horizontal component, and another function, q of x, y, for the vertical component. All right, and then, right, there's just a bunch of vectors. They're going to point probably in slightly different directions all over. And we want to figure out how much flow is coming out of a point is the divergence. Well, that's kind of hard to do. So instead, let's figure out how much flow is going out of a box. And then we're going to shrink that box to a really small point, and then that's going to be the divergence. All right, but we can figure out a box. That's not a point. It makes a little more sense to write that out. All right, so first thing is we need to define what this box is. So the center of the box is going to be at this point f of x, y. And then this picture is going to get pretty busy. So up here, it's going to have width of delta x and height of delta y. All right, so delta x, delta y. I've also put these together, so right, the horizontal direction, that's going to be the flux is another name coming for stuff flowing out of a surface, vector field flowing out of a boundary. So this is right, the left and right, and then the vertical one, that's the top and bottom. All right, so then next up is if we draw a box in here, sure, why not? Right, the vector field arrows are all a little bit different on the sides of the box, right? Because it has some width, it has some height. But we don't want to have to deal with that. That's a lot of vector field arrows to deal with. So instead, we're just going to approximate all the vector field arrows on a side with just the vector field arrow at the middle. So that's what we'll do here. So let's figure out, so let's see if I can get the right heights here. Okay, so we're going to have a vector field arrow on this side. It's going to vary a little bit as you move up and down the side, but it's an approximation. If delta x and delta y are small, then it's going to be pretty close. So this is going to be vector field arrow F. All right. And then we'll need the flux going out of all the sides. So we're going to need a vector field arrow on each side. So then that was this one. Let's go to here. It looks like the right height. So they're all going to point in approximately the same direction. Delta x and delta y are the same size here, maybe different lengths. Let's see then, flux going out of this side, that kind of looks like the middle. Okay. And this one. All right. All right, and then I got to figure out, okay, well, this is the middle, and it has width delta x and height delta y. Where are all these points? All right, because I need to evaluate the vector field at those points to actually get the actual vector. Right, so that's not too bad. So I've got F, evaluated that. Okay, well, it's at height y still. But if the box is delta x wide, and I only went halfway over, then it's going to be x plus delta x over 2, half the width. So x plus delta x over 2, comma, it's at height y. On this side, we have F of, this is going to be x minus delta x over 2, right? I went to the left by delta x over 2. So x minus delta x over 2, comma, height y. Then right here, I'll have to be a little clever. All right. Okay. This is still at x, comma, but it's a little bit lower vertically. So then if the height is delta y, then I went down half the height, so it's minus delta y over 2. Y minus delta y over 2. Okay. Then my last arrow, it might fit there. All right, F of, this is at still x, but now it's at y plus delta y over 2. Okay, that kind of fit. All right, so we had a box, it's fairly small, we have a vector field, the vector field arrows are changing on all sides of the box, but we're going to approximate the entire flow out of a side with just one vector field arrow in the middle. So now I got to define, okay, what is positive flow? So positive flow is flowing out of the box. So we're going to use dot product to calculate how much of the flow is going out of the box on each side. So I'm going to make a bunch of unit normal vectors. So this one is going to be 1, 0. On the other side, right, that's positive flow out. This one's going to go the opposite direction. So that one's going to be negative 1, comma 0. And then on the top and the bottom, we've got 0, comma negative 1 to point down. And then 0, comma 1 to point up. All right. And I want them to be unit vectors, right? Because if I take the dot product of the vector field F at that point with a unit vector, then that's going to be the projection of F onto that direction, and it's not going to change the kind of length, right? Because this is a unit vector dot product. All right, so now let's go ahead and calculate, okay, what is the flux on the right side? What's the flux on the left side, the top and the bottom? So now let's go ahead and approximate that. So we've got right flux, oops. Okay, so on the right side, I've got my unit vector pointing outward, so I have 1, comma 0. I'm going to dot product that with the vector field arrow at that point, so it's f of x plus delta x comma y, x plus delta x over 2, comma y. Then there's one more piece. So, right, I have the side of this box. I'm only using one vector field arrow, but, you know, if the box were a little bit taller or a little bit shorter, it's going to change how much flow is coming out of that side of the box. So I also want to multiply by the length of this side of the box to get the total flow going out, because I essentially have the same vector field arrow all along it. So that's going to end up multiplying then by delta y. That's kind of a triangle. All right. So that's the right flux. And then if we simplify that, well, we've got vector 1 comma 0 dot product with f. Well, if I dot product 1 comma 0 with f, I just end up with 1 times p plus 0 times q. Right? And then I have to keep in mind, right, I have to use the same coordinate. So it's going to be p of x plus delta x over 2, comma y, and then still times delta y. Right? The amount of flux going through the side changes depending on how long that side is. All right, so then we're going to do this 3 more times. So then on the left side, left flux, that one's going to be negative 1 comma 0 for that normal vector with positive flow out. Dot product f. That one's x minus delta x over 2, comma y, and then still multiplying by delta y for the side length. So negative 1 comma 0 dot product f, well, that's just going to be negative p plus 0 times q. So negative p of x minus delta x over 2, comma y. Then I've got the top flux, why not? Sure, yeah, let's fix it. All right, so top flux, I've got my unit vector is 0, comma 1. Dot product with f, which on the top is, let's see, x and y plus delta y over 2. And then I do have to multiply by the side length. In this case, it's delta x now. All right. So 0, 1, dot product f, we get 0 times p plus 1 times q. So it ends up being q. Evaluated at that point, so x comma y plus delta y over 2, and then still the delta x, counting for the side length. Then I have the bottom flux. All right. Okay, squished that a little bit. So that one's got the unit normal vector for outward flow, that's 0, comma negative 1, dot product f, evaluated at x, comma y minus delta y over 2, and then times delta x. Okay, dot product 0, comma negative 1 with f, 0 plus negative q, so negative q. Evaluated at x, comma y, minus delta y over 2 times delta x. Okay, I might just have barely enough room. I think I'll actually erase this. Okay. Okay, so now the total flux is going to be adding all the fluxes together. If I want the total flux out of this box, then I need to add them all together. But then that's going to be the total, so total flux. Oops. Okay, so that's going to be the right flux plus the left flux plus the top flux plus the bottom flux. So let's go ahead and do that. Yeah, sure. All right, so it's going to be p of x plus delta x over 2. Oops. There's a lot of writing for this. Comma y minus p of x minus delta x over 2 comma y, and then I'm going to put the delta y on both of those, and then plus I've got q times x comma y plus delta y over 2 comma minus q of x comma y minus delta y 2, and then that's all multiplying delta x. Okay. Right. So now the next thing is, okay, well, what I wanted to find the divergence at the point, the flux coming out of a point, essentially. So the idea then was to have this box shrink down to 0 height and 0 width. So essentially delta x and delta y go to 0, so the box shrinks and eventually becomes a point, xy. The problem with that, though, is that as the box shrinks, we have some thing in here, p of whatever minus p of whatever, times delta y. We also have plus q of whatever minus q of whatever times delta x. If delta x and delta y shrink to 0, we're just going to end up with 0 plus 0. So that's no good. Right, the flux coming out of a point, we don't want it to just be 0. Divergence isn't 0 all the time. So what we're going to do instead is we're going to define the divergence of f at x comma y as the limit, sure, whatever, as delta x comma delta y go to 0 as the total flux over the area of that box. So delta x times delta y. All right, so we're essentially averaging, okay, if the box gets smaller and smaller, the total flux coming out gets smaller and smaller, but then if you average the total flux coming out over the area, which is decreasing, we're going to end up with a divergence. All right, so if I write this out, I think I just have barely enough room. Okay, well, I'm dividing everything by delta x and delta y, so then I've got this bit. If I divide by delta x and delta y, the delta y here and the delta y here will cancel out, so I'll end up with this over delta x. So I can write that as limit as delta x goes to 0 of, all right, p of x plus delta x over 2 y minus p, ooh, hope we have enough room. All right, of x minus delta x over 2 comma y over delta x. The reason I don't have the delta y in here is it doesn't really matter. There is no delta y. It's all delta x's. And I've got plus the limit as delta y goes to 0. Here's where I make it a little scrunched. I have q of x comma y plus delta y over 2 minus q of x comma y minus delta y over 2. Barely made it. That's all over. Right, if I divide this bit by delta x delta y, I just end up, the delta x's cancel, I end up with delta y on the bottom. All right. So now we're almost to the final step here. I'm going to have to squeeze it in there. Okay. So the divergence of f, vector field at a point, x comma y, equals. So these look a little bit familiar, but they're written a little bit differently. So if you go back, this actually looks a lot like the definition of partial derivative. The difference, though, is that partial derivative, usually you have x plus delta x on this side, and you just have x on this side. Now, they're pretty much the same thing, right? If I have x plus delta x and x plus delta x and x, the difference between the two x coordinates is the total value of delta x. In this one, I have x plus delta x over 2, and I have x minus delta x over 2. The difference between these two is still delta x. So this is actually another way to define a derivative, a partial derivative. So this thing here, limit as delta x goes to 0 of p of x plus delta x over 2 comma y minus p of x minus delta x over 2 comma y over delta x. That's actually the same thing as the partial derivative of p with respect to x evaluated at the point x comma y. So there's half of it. And the next one, it's the same thing. Normally we would write the partial derivative of the coordinate y as x comma y plus delta y. And on this side we have minus q of x comma y without any deltas, delta y's. But it's the same thing here. The difference between this y plus delta y over 2 and this y minus delta y over 2, they're different from each other by a total of delta y. So this is another way to write the partial derivative with respect to y. So this bit here is plus partial q over partial y evaluated at the point x comma y. So there you have it. That's the intuitive explanation in 2 dimensions. So we started out, we had a point, we wanted to figure out what the divergence was at that point. Okay, that's kind of hard to just guess or come up with. So we started with a box that was centered around that point. It had a width of delta x and it had a height of delta y. We approximated the flux coming out of all the sides as the vector field arrow in the middle of that side times the normal vector for positive flow on each side. Oops. We added all those together to get the total flux out of the box. All right, total flux. And then, since the box, if the box gets smaller, the total flux will decrease. We decide to say, okay, well, the divergence is instead going to be the total flux over the total area of the box, and we're going to look at that as the box gets really, really small, shrinks to a point. Then we ended up with these 2 limit definitions. And they're not the way you normally write the partial derivatives, but this is a partial derivative of p with respect to x. This is a partial derivative of q with respect to y. And so the divergence ended up being partial p partial x plus partial q partial y. Oh, that was a lot of talking. All right, so it's similar in 3D, a little bit more complicated, but still similar. So we'll go ahead and do that next. I'm probably going to take, I don't know, I'll have to do some erasing when I'm doing that. So now for divergence in 3D, a lot more things to add together. So right in 2D we had 4 sides, and now 3D we have 6 sides to a cube. And so the divergence at a point we're going to approximate as the flux coming out of a cube, centered out at that point. It doesn't have to be a cube, it could be a rectangular prism, whatever. And it's going to have side lengths. So here I've got my right-handed axis, so x to y up to z. So this is actually the y-axis, this is the z-axis, and coming out of the board is the x-axis. And then we've got our box, and it's delta x, delta y, delta z for length, width, height. Then we had to update the vector field, right? So now we have f, which is a function of 3D coordinates, x, y, z, and it's got to have 3 functions now, p, q, and r. So we're going to do what we did before, and since I'm not a great artist and also gets really busy, I made this. All right. So we still need to make all the unit vectors for all the different directions. So I've kind of put this together. So you see red is this way, and that's red here, red here. And we've got the y direction, which is this one and this one. And we've got the z flux sides, which is the bottom and the top. And then on each of those, I have this unit vector pointing out for the positive flux direction. And then the other vectors here are going to be the vector field. So kind of same thing as before. We're going to approximate the entire flux coming out of a side, as we're going to dot product a unit vector for the positive flux, so perpendicular to the side, to the vector field arrow in the middle of that side. And then we're going to multiply by the area of that side for the total flux coming out. And then at the end, we're going to divide by the entire volume. So we're kind of getting the total flux per volume. Shrink it down, we end up with the divergence. Okay. There we go, that thing's fragile. All right. So let's get started. All right, so let's call this the left side here and this side the right. So it's going to be the y side. So let's start with x, sorry. So right, the front is kind of positive x direction. The back side is the negative x direction. So first we need to figure out, okay, what is the points in the middle of all these, right? So I've got that one, and that one, and that one, and one in the back here. Right? I guess there's one in the front. Getting a little too busy. All right, kind of, sort of reasonable. Let's take a look. So if I have the front of the cube, so the front flux. All right, so that's going to be the vector field evaluated at this point, dot product of the unit vector. So unit vector coming out of the front is pointing towards you, which is the positive x-axis. Sorry, so right, this little arrow right here. And so it's pointing that way. And so it's going to be 1 for the x direction and then 0, 0. So, right, there we go. It's going to be 1, 0, 0. Right, dot product with f. Evaluated that. All right, so if we start at x, y, z, we go forward half the length of the cube to get to the front. Then we've gone forward delta x over 2. So we've got f of x plus delta x over 2, comma y, comma z. Then we do have to multiply by the entire area of the front side. So it's going to be delta y times delta z. Okay, and we've got the back flux. Okay, the vector field arrow on that one, it's this one back here. And right, so it's going to have negative 1 for the x direction, 0, 0 for the y and z directions. Right, okay, so negative 1, 0, 0, dot product. That one we went backwards in x by delta x over 2, so it's going to be f of x minus delta x over 2, comma y, comma z. And the side, that area, is delta y times delta z. Okay, so that was the front, that was the back. Well, now how about the right and the left? So we got the right flux, which is in the positive y direction. I'm also going to have the left flux, which is in the negative y direction. So write those unit vectors. All right, this hasn't fallen apart yet. This one right here, so that's positive 1y, and then 0 and 0 for the x and z components. This one's going to be negative 1y, and, oh shoot, I have this, no, that's right. And then negative 1y, and then 0 and 0 for the x and z components. So, there we go, okay. Right flux, positive 1 for y, negative 1 for y. The other two components are 0. Take a dot product to get the flux flowing in that direction on that side, directly out of it. So here we start at x, y, z. We move forward delta y over 2 to get to the right side, and then negative delta y over 2 to get to the left side. So f of x comma y plus delta y over 2 comma z. Okay, that side length area. All right, I have it here, so this side's a little easier to see. So I have delta x along the bottom, delta z along the vertical part. So the whole area is delta x times delta z. Okay. All right, similar thing here. We get f of x comma y minus delta y over 2 comma z times delta x delta z. Okay. And now we've got the top and the bottom flux. And the bottom. Okay, so on that one, we've got the top one is positive 1 for the z component, and then 0 and 0 for the x and y. And on the bottom, it's negative 1 for the z component, and 0 and 0 for the x and y components of that unit normal vector to the sides. So that ends up being 0, comma 0, 0, comma 0. And then top is positive 1, bottom is negative 1. Dot product with f. Okay, the top one, we start at xyz, we go up by half the height. So it's going to be delta plus delta z over 2. Plus delta z over 2. Okay, the area of this side of the box, the top and the bottom, it's delta x times delta y. Okay, dot product f for the bottom one, that's x comma y comma z minus delta z over 2. And then delta x delta y for the area. Okay. Oh, fun stuff. All right. So now the total flux, all right, we're going to define the divergence at the point xyz. Divergence of f at the point x comma y comma z is equal to, well, it's going to be the limit, sure, as delta x comma delta y comma delta z go to 0 of the total flux. So adding all these together, but then we're going to divide by the volume of that cube, or box, or whatever. Well, all right, if we do that, the volume of the cube is delta x times delta y times delta z. And so, if we're a little careful, I think I have enough room. Okay, it's going to equal, okay, well, what if I take the front and the back, and I add them together, and then I'm going to divide by delta x times delta y times delta z. Well, okay, the front flux, we take 1, comma 0, comma 0, dot product with f. Well, we dot product 1, comma 0, comma 0. We get 1 times p, 0 times q, 0 times r. Add them together, it's just p. So we have p of, evaluated at the point, x plus delta x over 2, comma y, comma z. So that was the front flux, the back flux, negative 1 times this. So we end up with negative 1 times p plus 0 times q plus 0 times r. So that's going to be a minus p. And that one is evaluated at x minus delta x over 2, comma y, comma z. Okay, so but these had attached to them, right? Delta y times delta z on each one. But then we're dividing by the volume of the cube. So we have delta y times delta z times each of these. Then we're dividing by delta x times delta y times delta z. So delta y and delta z on the bottom cancel with the delta y and delta z on the top. So we're just left with delta x on the bottom. And I forgot a little thing here. Sorry, it's equal. It's the limit as delta x goes to 0. Right, I left off the delta y, delta z, because there is no delta y and delta z in here. But that's the first part. Then we need to add to that the right flux and the left flux, which is going in the y direction. If I do that, the same thing pretty much happens. So right flux, left flux, I have 1, I have negative 1 in the middle. So when I dot product there, I'm going to get positive q and negative q, and it's going to be evaluated at y plus delta y and y plus delta y over 2 and y minus delta y over 2. So it ends up being the limit as delta y goes to 0, because, right, I have delta x times delta z on both those, divided by the volume, delta x, delta y, delta z. The delta x and the delta z cancel out, and we're just left with delta y on the bottom. So it ends up being q of x comma y plus delta y over 2 comma z minus q of x comma y minus delta y over 2 comma z all over delta y. Then I also have the top and the bottom flux, so plus. This ends up being limit as delta z goes to 0 because the delta x's delta y's cancel. So that one top flux, bottom flux, I've got, 1 here, I got -1 there. Dot product of those, I end up with just r's. It ends up being r and then -r. Add them together. We end up with r of x comma y comma z plus delta z over 2 close minus r of x comma y comma z minus delta z over 2. Okay, those are multiplied by delta x, delta y. Divided by the volume, we're left with just delta z on the bottom. All right, and now again, those are all definitions of the partial derivatives. All right, they're written a little differently. Instead of p of x plus delta x and just p of x on the side, it's p of x plus delta x over 2 and p of x minus delta x over 2. They have a difference of delta x in their two x inputs. We have a delta x on the bottom. Take the limit, delta x goes to 0. The first component of the divergence, that was a terrible triangle, divergence of f at x comma y comma z, that's going to be partial p partial x. And the next one, that's the definition of partial q partial y. And the last one, we're in 3D, that's the definition of partial r partial z. Whew. So, there you have it. Doing a lot of careful accounting and dot products and evaluations of the vector field at different points. We figured out the flux coming out of this box. Each side of the box was perpendicular to either the x-axis, the y-axis, or the z-axis. And then we averaged the total flux coming out of the box, divided by its volume, and we end up with the amount of arrows kind of coming out of a point averaged over the size of that box, which is the divergence. And then the divergence in 3D is the sum of the partial derivatives of each of the components of f. Partial p partial x plus partial q partial y plus partial r partial z. So there you have it. That's kind of an intuitive explanation and derivation of why the divergence has its formula.